computer share. Hello, class. I hope you've been having a wonderful week. Actually, it's Monday, so it's just the beginning of the week. So let's pick this up. So I know it's been like we're on this session is recorded on September 27th. We're studying a little bit late, but the midterms are actually approaching, and it's important to do like have the right approach to do well at UBC. Because remember, like it's just working hard is not enough to get a good grade at UBC. Everyone is like good student, and there's going to be like they expect the average to be at a certain level. So if you don't know what to look for in a question, and if you're not approaching the questions in the right way and also not practicing the right way, you're not gonna be able to do well at UBC. So not only you need to know how to answer the questions, you need to be able to do them in the right time. Because a lot of times I've had a lot of students who said that, yeah, I know everything, but I ran out of time. So that's why in our approach, we're gonna actually help you tell you like how to approach and search for the things that matter to you in the question and how to answer them. Because when you actually read your chirp, a lot of it is actually like theoretical, and they may explain it like what it is, but it doesn't actually tell you how to approach the question. So that's literally my job. I'm gonna actually help you get this right. I'm gonna give you a lot of like detours, like how to like answer questions like in a much faster way. So this is going to be the key. If you guys have any questions about the content of this video, you're welcome to post your questions on the Discord. And then at the timely matter, we're going to get back to you. So yeah, let's get started. So CHEM121. And also it applies to CHEM111, I suppose, but CHEM111 students will catch up later. So when you're actually talking about the CHEM121, the first part is like pretty general, but on the other hand is also very important. So when you actually look at your chirp, it's going to be like starting with like compounds. So when we say something is a compound, it's just anything. It's just like bunch of atoms connected to each other. But then you wonder, why is your definition so broad? It's because you can use like so many different types of atoms using different types of bonding to connect them together. But the bonding is going to be intramolecular bonds. So you see, again, we're going to talk about intermolecular bonds later, but intramolecular bonds are the bonds that are within the same molecule. So you use you use it to connect the atoms together, so you end up getting the compound. So the most common examples are the one that you like come to your mind right away because you've been doing like trying to like answer all those Lewis structure questions is covalent bond. Another one that you have to deal with in this course, and maybe if you're taking biology 112, is actually ionic. And the one that is you just need to know what it is, but you don't have to deal with it, is actually the metallic. So before we even get into too much detail, let's actually talk about the metallic, because this is super short and this is all the information that you need. So this one is actually used in this one. So if you actually go to periodic table, maybe I should just take a picture. So by the way, this website is actually very helpful because it's not a picture. So when you're looking for an element, you can just Control F it and it just shows up. But anyways, so we're gonna talk about like how different atoms are bonding to each other. But the transition metals, which are these red ones, use metallic bonding. Like when you have a piece of like your laptop, your MacBook, which is made of aluminum. Actually, aluminum is here, so never mind. But transition metals, like metallic stuff, they actually use metallic bonding. That's it. That's all you need to know. And what is the metallic bonding? Metallic bonding is actually when all these atoms are connected to each other, and it's a sea of electron. So it's kind of like everyone is sharing their electrons, but it's not just between two specific atoms. It's like this guy loses his electron and it shows up like somewhere else at the other end of the rod of the like copper or something. So it's actually pretty, it's actually a sea of electrons. And that's all you need to know. Done. So, but then we actually have to talk about covalent and ionic. And before we talk about it, so you see, like, I mean, you probably even remember it from high school, that is about sharing electrons. And ionic is actually about one takes and one gives. So it's about redox. So why redox? You're like, oh my God, I don't remember what redox is. No. Redox is just something that gets oxidized, means lose electron, and someone that gets an electron, which is reduced. That's all you need to know. But so that means like it's someone that is like got the electron, which is a negative, and someone who lost the electron because what do you think this guy's got this electron from the guy that turns positive? So these are requirements. Again, in biology 112, again, it's the same idea too. You have to find someone which has a charge. But then you guys are like, well, how do I know? Like, how do I differentiate these guys? Like, how do I know like these guys, like when I put this guy, this atom and this atom right in front of each other, this guy is going to steal this guy's electron, or they're going to be just nice and they're going to share the electrons and live happily ever after? Like, how do I know? And this is actually boom, boom, boom. So it's actually related to electrochemistry. I know. So what is electrochemistry? Electrochemistry is actually a very simple thing. It's the power, like how much grip an atom has on its electrons. That's literally what it is. So how much grip an atom has on its electrons. Not even on its own electrons, any electrons that is surrounding it. So surrounding electrons, maybe that's better, on its, so like, yeah, so surrounding, yeah, I forgot what it was. So surrounding electron cloud. So you need to, for this course, you're going to learn other trends as well. But for just for today, you need to know the trend for electrochemistry. So, and what this thing is, so you see, if this is group 18, which is like all the noble gases, and this is group 17, which is like all the halogens, the trend is it increases from here to here. So what does it mean? It actually increases both in left to right and top to bottom, bottom to top. How do I personally remember it? It's very simple. I know the most electronegative element in the world is fluoride, which is actually the same thing that I just showed you. So as you move towards the fluorine, it becomes more electronegative. Simple. So you're like, okay, well, how is it related to this whole thing? Like, what does it have to do with ionic and covalent? So you see, this is the difference between why you pay me and like our group and just going to your class. So you see, when you're actually talking about ionic, so ionic interactions, it's not about being nice, it's about bullying someone. The guy that is someone is a lot stronger than the other one. AKA someone is a lot more electronegative than the other one. So when you actually put these guys to each other, the imbalance of power, AKA electronegativity, causes the one that is being bullied to lose its electron to the one that is actually the bully. So that's why, like in ionic interactions, someone loses like an electron and turns positive, and someone gains the electron and turn negative. So that's pretty much the reason. So, okay, now, so you're like, okay, so what's the threshold? Like, how different they need to be for me to consider for them to be like for them to be known that, oh, so this is the threshold, okay, they are going to share, but from this point forward, oh, they're just such a big imbalance of power. So how is that going to work? So you see, this is not, so if you actually look at the periodic table, so as I told you, as you go from this point towards this point, so obviously when you have a lot of the atoms that are on the far right and atoms from the far left, they would have very different electronegativity. So that means that's probably what you would actually, like, those are the guys that are actually involved in ionic interactions. So you see, for example, if we actually use group 1 and 2 and maybe group 16 and 17, then that's probably going to be the groups that actually do the clashes and stuff. So you have to be, those are the guys. But you're like, am I probably, or no? First of all, there's actually a numerical threshold that you don't need to know for this course. So that's what it is. But for your sake, again, you're like, can't I just rely on seeing the positive and negative charge? And the answer is no. In biology 112, when you're dealing with these things, they don't expect you to know much chemistry, the very basic thing. So when there's an ionic interaction, they show you the negative and positive charge as well. But for this course, that's not going to be the case. You see, they're going to actually hide it. So for example, can you see an, so like ionic, like example would be like NaCl. Do you see a charge? There's no charge. The positive charge of the Na is being covered by the negative charge of the Cl. So unless from your own understanding, I haven't, by the way, got to how you identify the ionic interactions though. But again, my point is that you're not going to see actual charges to say, oh, that's an ionic interactions. This is not that easy. So you're like, okay, so what's the approach? Can I just say like specific groups and stuff? You see, as I told you, we need positives and negatives. But we never discussed, okay, why would someone become negative and positive and by how much? This is actually very important. So you see, when I actually put like these noble gases are the idols, the goals, like everyone, all of these guys love to be these guys because they're in peace. You know, like when you actually make a reaction is because you're not in peace, and when you make a reaction, you turn more stable. These are all stable. Why? Because they have the right number of electrons. So everyone else do their things to become these guys. So why am I talking about this? Is because in order for you to figure out like what the chart, who loses charges and who gains, who loses electrons and who gains electrons, is very simple. It's pure based on how close they are to these guys, and also if they're electronegative and or not. So two things. You expect these guys to be very electronegative, so they're usually negative, and these guys to be very positive. But we can actually look at it from another angle. Look, when we say something's charge, it's actually the number of protons minus the number of electrons. So you see this F, how many electrons is it away from this neon? 1. So 1 electron. So if it actually gains 1 electron, it turns into a neon. Well, with 1 fewer proton though. But I mean, as far as the electrons goes, it's in peace, which is great. How many electrons does this oxygen need? -2. This one, -3. Usually the charge on these guys are this. Are they always charged? No. Sometimes they are, sometimes they're not. So you're like, then what is, so this is still not concrete. I need a concrete way to answer the question on the exam. When they give me something, I want to use this method to like easily find out like what the ionic interactions are. And it's actually very simple. You see, these guys may have a lot of like ifs and thens, and maybe I'm charged and maybe I'm not charged. But well, you have some people, like some atoms that are always positive. And who are those guys? These two groups. You see, this lithium is actually has like, let's say 3 electrons. How many electrons does it have to lose to become helium? 1. All of group 1 elements are +1, always. They are never neutral. If you see them neutral, it's because there's a negative that covered them. So that's the idea. And all the group 2s, they have to lose 2 electrons because, like, for example, this beryllium needs to lose 2 electrons to become helium. This magnesium has to lose 2 electrons, so 12, to become neon. So you see, so in order for you to actually find like ionic interaction, you need to have, you're going to need to, like, in your whatever compound is going to be, so the positives are going to be group 1 and 2. So you're like, well, if it is group 1 and 2, does it mean like, so whatever, so when you actually say, let's say you have a sodium here and then you have X. Well, you know sodium is positive actually. It's just being covered by this X. So this X is actually -1. Because like the overall charge, I don't see any charge here. So if this is +1, which I know it's 100% of the times it's +1, so this one is, you have 1 of it, and then also it canceled the +1 of this one, so it has to be -1. So you see, I already know this is ionic just because of this sodium. So for example, like we have like Na, SO4 2. Again, you see, I know my Na is +1. So there's 2 of it, so it's +2. So this whole thing, the charge has to be -2. But again, this is this whole activity of like doing questions and okay, figure out like what the charge is. We're gonna like practice in future sessions. But we are, so I'm just telling you like the fact that this guy is positive, so having these group 1 and group 2s mandates, unless, and if the overall compound is neutral, it mandates the other guy to be negative, and that actually meets the criteria for ionic, which we need a positive and we need a negative. But again, that negative and positive charge don't have to be visible to you. So this is the key. You don't have to be able to see this. And then usually the negative guy is usually group 15, 16, and 17 elements. Again, but how you figure out what their charges are always based on group 1 and 2. So again, I told you, oh, F is usually -1 and this is -2 or this. Or like S is actually, I told you S or like the group 16, they're usually -2. Well, this guy happens to be -2. You're like, how do you know this is the guy that actually holds the charge? Actually, it's not. This is the overall compound, but that's for another day when we actually start doing Lewis structures. And you'll see that like how easy it is to do those questions. Like so you technically, like the chirp method for Lewis structure is very long and I don't believe in it. I don't use it at all. I have my own method, which is a lot faster. So anyways, to sum it up, when you have, in order for you to identify ionic interactions, the first thing you need to do is to see whether you have a group 1 and group 2 or not. After you checking it, is it neutral or not? If it's neutral, it means there's a negative to cover it. And if there's a negative, that's ionic. Simple. See, that's how you answer it, by knowing what to look for, not just by following the scientific definitions and those things. Those are not helpful for answering questions in less than 1 minute. So yeah, so that's how you do ionic interactions. So then you're like, well, what is this salt that they keep talking about? You see, salts are compounds that have ions in it, that have ions. So technically that's a salt. NaCl is the most common example of a salt, but technically NaCl, Na and Cl. So positive, negative, check marks. It actually meets our criteria for ions, which is like you have negative and positive. But again, you need both of them. So if you have both of them, so it's a very common type of question that come up on exam too. They're saying like identify a salt. Again, you need a positive. Who is usually positive? Group 1 and 2. Then you look for your negative. If it is neutral, then there's a negative. And that actually, then congratulations, you have a salt. So simple. You see, when you know what to look for, nothing is difficult. It applies to any topic that you do, especially at UBC. So always, that's why it's not about working hard, it's about working smart. And considering that most of you guys are taking 4 or 5 courses, you will have time issues because you will be spending too much time on one course, and you're not gonna have enough time for other courses. So that's check mark for metallic and ionic. But then we're like, well, are we done? Well, not necessarily. There is like one little thing left. You see, when we're actually talking about these ions, they create something called lattice structure. So this lattice structure, what is this? So lattice structure is like this, like very organized structure, where it's just repetition of these ions, where they create ionic bonds with each other. And based on based on two factors, this structure can be more stable and take more energy to break, or less energy. So I'm just showing you an example. So you see, this is like a lattice, so crystal structure. They create a crystal structure, lattice structure, same thing. And the amount of energy, so lattice structure is a structure that is made by ions bonding together. So, by the way, it's very important for you guys to listen to me, because I don't think many of you guys can actually read this. So yeah. So lattice structure. But and then lattice energy. So that's lattice structure is just, you just need to know that. But lattice energy is actually the part that we are concerned with, like we actually care about in this course. So lattice energy is the amount of energy needed to like, let's say, blow up, like to break. Let's not be too dramatic. Break up a lattice structure. So again, what are we concerned with? So you see the formula that you actually see for this in your chirp, like in chapter 2, is actually something like this. It's the formula they give you is actually not for calculation, but it's mostly for like seeing the relationship between the factors that affect the lattice energy and like how it's actually used. Is it like directly proportional, inversely proportional? Like that's what it is for. So the energy, the lattice energy, is actually proportional to, so that's what it means. It means, like, for example, N times M, where the N is the magnitude of charges, like charge of positive ion, and then M is the magnitude of charges of negative ion. And then it's actually the radius of N to M. Like, I mean, let's say X to Y, and then R, X to Y is the radius between the two ions. So pretty much based on what we are looking at here, so the conclusion, all you need to understand from this, again, we're never going to use this formula for mathematical reasons, at least for this course. I'm sure we use it for some course. Is that so so it means that the bigger the charges of the ions involved in the lattice energy, lattice structure, and the smaller the distance between the two atoms. So I mean, the smaller the distance between them comes from the radius, right? Because let's say this is X and it has like this radius, and this is Y, which has this radius. So it has to be like, if it was like had a smaller radius, it could have actually got closer to this one than if it was actually bigger. So you see, like now at the rate, so because the distance between the two is the addition of the radius of the two. So that's why it's actually not a good thing. So yeah, so you want the radius to be as small as possible, and the charges of the two to be as big as possible. So again, this is going to be by far one of the easiest questions on your midterm and final. So you see, when it comes to the moment you see a lattice energy question, it's going to be like two factors we know. So it's charges and radius. But first, you actually look at the charges. Then you look at the radius. Because first, you're going to rank them based on the charges. And then you're going to have some of the ions that have the same charges. And then you look at the radius of those guys that have the same charges. So you don't look at them at the same time. When the only time when the charges are the same, then you look at the radius. So that's how you approach it. So one, so you look at the sum of the magnitude of the sum of the magnitude of the charges on the ions. So you see, so for example, how do we look at it? Let's say, for example, there's an NaCl, and there's like a Ka, like B, I mean, let's look at it like, so let's say KaBr2. Sure, that works. So again, we know that always the charge of the positive guy. It's like +1, and this one is +2 because it's grouped under, it's on group 2. So what does it mean? It means that you can actually put this here. Like, what's the charge of like on a Cl? So the Cl is actually -1 because it's neutral, so it has to be. So anyways, so are you, well, I mean, you're like, if you sum them up, it's +1 and -1 is always 0, and then this one is minus, so it's -1 actually. So, but it's like 2 of it, so it's like -2, so stuff. First of all, we don't care about the number here. We only look at the plain number of the charges. So, but the way, so that's why I said magnitude. Like in math, you know, like the charge doesn't matter. So it's like +1 and then -1, but it's like 1, 1, so it's 2. And this one is 2 and 1, so it's 3. So the lattice energy needed for CaBr2 is greater than NaCl. So you see, I didn't look at the radius at all. Why? Because I didn't need a tiebreaker. You only use the radius for tie breaking. So now let's look at, like, what if, for example, we look at something that has equal like sum of like charges, and then we look at the radius. Again, so look at the radius only if if number one does not work. So smaller radii, like higher lattice energy. So what happens here is this. So smaller radii is this. Okay, so let's say like we're looking at NaCl and KCl. So let's do the charges again. So when we look at Na and Cl, they're both on the group 1. Again, you're like, how do you know? Can I just always rely on periodic table? First of all, again, you can. You're going to be given that, but again, technically, if you have done enough practice to do well in a midterm, you should know these things by heart. So it's going to be +1 and then -1. So the overall is just 2. And then it's going to be +1 and then -1 is overall 2. So the first method didn't work. But then you're like, okay, well, you didn't actually tell us what the trend for radius is. You're absolutely correct. Now I'm going to tell you. So you see, the electronegativity increases in this direction. The radius increases in this direction. So fun. So you see, so okay. So what does it mean? It means that as you go down and left, it increases. So let's actually, so by the way, they're the same for Cl, like identical. And then let's compare the Na and Cl and Na and K, and whichever one that is actually smaller is going to have a greater lattice energy. So let's look. So Na is here and K is here. So K has a greater radius, but we're looking for a smaller radius. So we have a winner. So NaCl has a greater lattice energy than KCl. Just like this. But then you wonder, well, what if they were both different? So it was like Na, let's say, NaCl, and like let's mix it up, like Br and then KCl. We already know Na is smaller than K, but let's compare Br and Cl. So Br has a greater radius than Cl. So you see there's a mixed message. Do we actually get this type of question on exam? No. If you're meant to compare the radius, it's only one of them switching. So you can easily use the trend to answer the question. So it's actually pretty straightforward. So first compare the charges. Again, look at the magnitude. So it's -2, you still look at it 2. And then add them up, and whichever one has a bigger number. And then when you actually have, if it is actually a tie, then we look at the other factors. Simple. So yeah. Right. So then so that was it. So that was everything about ionics. So to sum it up, so for ions, we need a positive charge and a negative charge. positive charge and a negative charge. So for the positive charge, you just need to use the group, as like the moment you see group 1 and group 2, and then the overall molecule is just neutral, it means that, well, group 1 and 2 is always positive, so there's someone who is hiding the positive charge by being negative. So the other thing that this group 1s and 2s are connected to has to be negative. Well, the moment you see that, that actually meets our ionic interactions. That also meet our salt definition, which is just means that a salt is just two ions of one positive and one negative, that they're connected to each other through ionic interactions. So simple. By the way, just for your information, you're like, because some people actually confuse this, and many people have asked me this before, what's the difference between if these are intermolecular, what are intermolecular? And intermolecular, again, this is going to be part of this course. We're going to talk about them later. If you're taking biology 112, you're actually talking about them right now. And I wish you good luck on your midterm. But those are actually hydrogen bond. Depending on if you're in chemistry, it's called dipole-dipole and London dispersion. In your biology course, the same things are called permanent dipole and induced dipole, in addition to hydrogen bond. So yeah, so those are intermolecular, and those actually happen between molecules. So one molecule here and one molecule here, they make interactions with each other. They're more like interactions. These are like very strong bonds, and these are like stronger than those ones. So yeah, easy peasy. So now we don't have that much time to cover this in this lecture. So what we're going to do, we're going to actually do a bunch of examples to talk about. So before, but actually let's talk about, yeah. So let's talk about some practice questions to get started. Okay, so let's say, so we're actually interested in like figuring out what the charges on the following compounds. So you see, let's start with like an easy one. And I'm going to give you a pause. And then like when I do a question, like when you see a question, just when you have seen it, just pause the video so you can actually do it, try it yourself. Because again, if you're just going to watch me do it, you're not going to be able to do it yourself. There's 0% chance, because you need to have done it, make the mistakes, and then learn from the mistakes so you won't repeat them on your midterm and final. That's the only way. And also, but with practice, you tend to do it faster and faster and faster. So let's start with an easy one. So let's say K, F, and then we have M and N. So a lot of times, like, again, I've told you many times, the charge of the negative one might change, but the charge of the positive one always stay the same. And I've said this before, that like the charge of the group 1 is always +1, with the exception of hydrogen. Hydrogen can be positive, but that's going to be later for future. And beryllium and all these group 2s are going to be +2. So when I actually saw like K, so the charge of the M is of course +1. But then you see no charge up here. So that means that this guy, and you know, like the charge of the K is like +1. So and then the F, the charge is -1. So M is not +1. So the charge of the K is like this and then minus this. So how many do I need? Like we always go for the least number so they cancel each other. And that is going to be like K1 and then F1. Simple. So we're looking for like how many do you need for each to cancel each other. So now let's do, for example, beryllium. No, yeah, that's not beryllium. That's what do you call this? Barium. So barium M and then SO4 N. It's like, yeah. So again, so we know barium is +2, and SO4, again, you should know it, it's -2. So again, so the M and N are both. So pretty straightforward. So, but let's talk about like some other variations. So let's say K CR207. And yeah, and then MN. So you should know at least that CR207 is actually -2. And this is +1. So how many Ks do you need to cancel one CR207? Is actually 1. I mean, sorry, 2. And then N is going to be 1. So what else? Let's say, oh, let's do it like an interesting one. So that's like, this is like a bit more challenging, but not really. So it's like Mg PO 4. So as you might know, this the charge of the PO4, again, you see none of these have charges because they're being canceled by each other. But the charge of the PO4 is -3. The charge of the Mg is +2. So obviously they're not going to be crossing like by this. So maybe we should go up to 6. So we need to have like 3 here and 2 here. So that's how it works. So there's like a short list that you need to know, like for these things. Obviously the group 1 and 2s are very obvious, but these ones, PO4 and stuff, they're like a very short list you can easily memorize, which you kind of need to know. So yeah. So another example would be Mg NO2. So you might know, or I hope you do, is that +2 and this is -1. So how many do I need? So you actually need 1 Mg and 2 NO2s. So you see, so you have to memorize like some of these guys, which should probably memorize their names too, like nitrate and phosphate. And like if it's just like this, is fluoride. I think it's you learn in chemistry 11 or something like that. Yeah. So let's actually do a let's do another question and then we wrap it up. So I'm gonna give you a bunch of things, and then I'm gonna ask you like which one is gonna have the highest lattice energy. So highest lattice energy. So it's like NaF, NaCl, Kf, MgO, and BaO. So So let's actually do this and then we're pretty much done. The next topic, by the way, that we're going to cover is going to be covalent bond. But I thought that it's since it's such a big, like massive topic, it's better to actually dedicate like an entire session to it. So I didn't want you to actually like hear something and just gets confused, and then until the next video is posted, you're going to be confused, and that's not going to be very ideal, I guess. The worst thing that can happen to you is like getting like misunderstandings instead of actually not learning, because that way you actually think you got it and you stop learning. So you see, this is like, oh my god, that's like a lot of the like ionic compounds. Like, how am I supposed to do it very quickly? You see, again, we have to figure out like what's the sum of their charges. So Na is +1 and it's being neutral, so it has to be -1. So 1 plus 1 is 2. We already did NaCl is like +1 and then -1, so 2. Again, Kf, K is 1, F is -1, so it's 2. So Mg is +2 because it's on group 2. And it's actually, the whole thing is neutral, so the O has to be -2. So it's actually 4. And then barium, not beryllium, and O. So again, so beryllium is +2, and then O is totally canceled. It is actually canceled its charge, so it has to be -2. So it's 4. So you see, like right away, I know these two are actually have higher lattice energy. See, that's knowing what to look for. Then I look at it. Okay, so they're identical with the O, but which one has a smaller radius? So I look at it, and then like, oh, so barium is here and Mg is here. So as we discussed, as you go to the bottom corner, like francium has the greatest radius in the world. So Mg has a much smaller radius. So it's a lot. So that's causes the greater lattice energy. So that's why our winner is MgO. So you see how little time it took? Is because if you know what to look for, it's never difficult. So that's it. Again, if you, after watching this video, please please ask any question that you have on the Discord chat, and then maybe like I'll try to get back to you like as soon as possible. And maybe even like, and please don't send me private messages, because maybe your question is someone else's question, so that way it becomes a community, and your question can help other people too. So yeah, have a good day. Bye.